One-dimensional diffusion of an atom. Consider a thin copper wire stretched out along the x-axis. A few of the copper atoms located near x equals 0 are made radioactive by bombardment with fast particles. When the temperature of the wire is raised, the atoms become more mobile. Each atom can then jump to an adjacent lattice site, either to the side on its right in the positive x direction, or the side on its left in the negative x direction. The possible lattice sites are separated by a distance L. Assume that one has to wait a time tau before a given atom jumps to an adjacent lattice site. This time tau is a rapidly increasing function of the absolute temperature of the wire. The process whereby the atoms move about by virtue of successive jumps to adjacent sites is known as diffusion. Suppose that the wire is rapidly raised to some high temperature at some time t equals 0 and is thereafter maintained at this temperature. Let p of x dx denote the probability that a radioactive atom is found at a distance between x and x plus dx after a time t. We assume that t is much greater than tau for all times t of physical interest, since tau is quite short when the temperature of the wire is high. Make a rough sketch showing the behavior of p of x as a function of x shortly after t equals 0, after a moderately long time, after an extremely long time. What is the mean displacement x bar from the origin of a radioactive atom after a time t? Find an explicit expression for the standard deviation delta x tilde of the displacement of a radioactive atom after a time t. Now you might have noticed that this problem is in a way similar to our random walk problem. An atom can jump either to the right hand side or to the left hand side. So if you have the wire stretched out like this between minus L and plus L, so we have a wire length 2L, let's say, and you have an atom here right in the middle at x equals to 0, this can jump with probability p to the adjacent side on the right or to the adjacent side on the left, and these sides are at a distance L from the origin, and then we have another L, etc. So we have adjacent sites at a distance L, and we have a completely random motion of the atoms, so the probability of an atom moving to the right is p probability of right jump, and q is probability of a jump to the left jump, and p and q are equal to 1/2. We have equal probability of moving to the right or to the left, as there is no preference. Okay, and what I should note here is that first of all, I would like to start out solving this problem from part B and C, and then I will move back to part A because it will be easier to see the functional relationship to make a rough sketch. So for part B, first I would like to know that for a given time interval t, I can count how many total number of jumps I can have. Since each jump takes a time tau, so one has to wait a time tau before a given atom jumps to an adjacent site. This is telling me that there will be a total of n, capital N, which is t divided by tau jumps. Okay, and So that's one thing to note here. So the number of jumps is t over tau. And the other thing is, since the radioactive atom can jump to the right or to the left with equal probability, we will find that for the probability distribution function, probability of having an x value for the displacement is the same thing as having a minus x value for the displacement. That means the probability distribution is symmetric around x equals to 0. So we should expect a symmetric distribution around x equals to 0. And once again, I call n the number of jumps to the right. I call n prime number of jumps to the left, and n plus n prime is equal to capital N, total number of jumps. And then I have n prime is equal to capital N minus n. Then I can talk about the total displacement to the right, the net displacement or the total displacement to the right, which I call x. This will be x is equal to net number of displacements to the right, n minus n prime, times L. And since n prime is equal to capital N minus n, it is 2n minus capital N times L, which is basically telling me that x is equal to 2n minus t over tau times L. Okay, so I have these three conclusions. And based on this, because for a given n value, I have a one-to-one correspondence between n and x, I see that is similar to the previous problem on the random walk. If you talk about the probability distribution function of x, it should be the same thing as for n, which is also the same thing for n prime. So because there is one-to-one correspondence between n and x. So given an n value, we have a corresponding x value. There's one-to-one correspondence. So we will find that since we have probability distribution function and even function, probability of x is equal to probability of minus x. If you calculate the mean value of the displacement, this would be over all possible x values starting from minus L to plus L, probability distribution function x dx. Now here I have argued that this is an even function and here I have x which is an odd function. So basically for p of x, that means it is p of x is equal to p of minus x. Here we have f of x is equal to x, f of minus x is equal to minus x, which is minus f of x. So that's the odd function. So you multiply an even function with an odd function and integrate it symmetrically around 0 over all possible values of x. The integral will give you 0. So basically we find that the mean value of the displacement has to be 0 because we have the multiplication of an odd function with an even function for a wire of total length 2L. And here basically I'm using the definition of the average value. You multiply the variable with its probability distribution function with its probability and go over all possible values with their corresponding probabilities in the summation or in the continuous version integration. You find the mean value. So we have the mean value of x is equal to 0. It has to be a symmetric distribution around x is equal to 0. So the integral gives us a 0 at the end. So that's the answer to part B of the question, mean displacement from the origin of a radioactive atom after a time t. Now find an explicit expression for the standard deviation of the displacement for a radioactive atom after a time t. So let's talk about the standard deviation in the displacement. Well, the standard deviation delta x tilde is by definition a square root of the deviation delta x square average value, or it's also known as root mean square. And the deviation of delta x from the mean value is x minus x bar, and here we have found that x bar is 0, therefore the deviation from the mean is equal to x. So we find that delta x square bar is basically x square bar, and so the delta x tilde, the standard deviation, must be equal to square root of x square bar, the average value of x square. Now what is this square root of x square bar? So that's our question here. Now if you go back to where we have found the relationship between x and n, if you remember, x is equal to 2n minus capital N times L. Capital N is equal to t over tau. So basically square root of x square bar is square root of 2n minus capital N square L square average value, because it was 2n minus capital N times L. So here it is, and this is going to be 2n minus capital N parenthesis squared L squared average value. So L square is just a constant, its average value is L, so it's L times square root of 2n minus capital N square average value. Okay, so we need to find what this is. All right, so I would like to talk about the mean value of n, so let's leave this for a moment here and go back to the discussion on n instead of x. So we have x bar is equal to 0, which means we have 2n bar minus n is equal to 0. So the mean value of n is equal to mean value of n prime, which is capital N over 2. This is equal probability of a jump, equal probability. So P is equal to Q is equal to 1/2. Remember, P and Q I have defined as probability of right jump and left jump. So these are equal, so it's the same. So I find that n bar is equal to the total number of jumps times P. And if you remember our discussion in the lecture about the ideal gas problem, this is actually similar to that. If you have a mean value of capital N times P, you can see this as N by defining N as a summation over I from 1 to N Ui, where Ui is 0 with probability Q and 1 with probability P. So Ui is a number for the ith step. It can be a step to the right, or it can be no step to the right. So it's basically I can think of the net number of steps to the right. If there is a step to the right, it is 1. If there is no step to the right, right jump, no right jump. Okay, so the probability of the no right jump is equal to Q. Okay, so n is going to be the total number of right jumps. For each step, I'm calculating the probability, basically counting over all possible values of Ui and multiplying it with their probabilities. I get the n bar value. So I have for this one, sum over I equals 1 to n Ui bar, where Ui bar is equal to 0 times Q plus 1 times P, so it is P. So adding over all possible values from 1 to n, I get n times U bar, which is n times P. So the mean value is capital N times P. For the number of steps to the right. Okay, so then for delta n square bar, the variance, I have n minus n bar square average. That's the deviation from the mean, and this is basically n minus np square average. And this can be calculated by writing basically delta n square bar is equal to sum over I equals 1 to n delta ui square bar plus sum over I equals 1 to n j equals 1 to n, I is not equal to j, delta ui, delta uj bar. So we have done this calculation explicitly in the lecture, and we have found the result for this calculation was that delta n tilde was equal to square root npq. So you can go back to the lecture all about the ideal spin system where we have done this calculation, and you will find that where n bar is np, delta n tilde is square root npq. So this was basically the same calculation that we did in the lecture. So Delta n tilde is, on the other hand, in our case, n minus n over 2 square average value square root. So this is equal to square root npq. So what I need here is the 2n minus capital N square bar square root. So that's basically what I'm after here. So you can see that this is basically square root n times 1/2 times 1/2. So this is square root n over 2. So we find that n minus capital N over 2 square bar is equal to, if you squared both sides, is equal to capital N over 4. So this will imply that I have 2n minus n square over 4 average value. This is equal to capital N over 4. The 4's will cancel. So 2n minus n square bar is equal to n. So substituting this to what we are trying to calculate here, we find that square root of x square bar, which is delta x tilde, is L times square root of 2n minus n square bar, which is square root of n. So delta x tilde is L times square root t divided by tau. So you can see that this deviation, the standard deviation, will be increasing with time as L times square root t over tau. Now I will also put a link here to the corresponding lecture where we have done this explicit calculation of n bar and delta n tilde, so that you can easily review what we did in the lecture. But whose result I'm using here. So basically, I should remind you that what we have here is, because this is the same thing as the random walk problem, only in the continuous limit, so we can put as a remark here, this probability distribution for n will actually be given by the Gaussian distribution, which is 1 over square root 2 pi delta n tilde exponential minus 1/2 n minus n bar divided by delta n tilde square. So this is basically our Gaussian distribution. So we have shown in the lecture that the binomial distribution will turn into the Gaussian distribution in the continuous limit. So answer to part A. So if we were to plot this for the probability distribution of x, probability distribution function of x as a function of x, I'm assuming I have a wire that is stretched out between points minus L and plus L here. So for at t is equal to 0, I'm going to have almost no distribution. So shortly after t is equal to 0, which is shortly after the time t equals 0, that's part 1, I'm going to get a very sharp stretch a very sharp function here which is symmetric around x equals 0. So I'm going to get a Gaussian distribution which is symmetric around x equals to 0. So let's see if I can do a better job here. Okay, so this is going to be a rather sharp Gaussian function, and it's going to have a distribution of 2 times the standard deviation here, 2 times delta x 0 tilde, so that's in the first case. So this is in part I, and then if I wait a little bit longer, you can see that the delta x tilde is increasing. So after this we're going to see another distribution, so we can sketch this one. So the probability distribution function between minus L and plus L. So this is going to be stretched out more. So you will have a distribution like this. Again, symmetric. This is for delta x 1 tilde, let's say, that is greater than delta x 0 tilde. So you will have a larger full width half max. And then, so that's part II. If I wait for a very long time, what will I see? If I wait for a very long time, I will see that the atoms have diffused to the left and to the right, and basically I will see a more or less uniform distribution here. Here I have assumed that it's not complete yet, so we will have a more or less uniform distribution for t much greater than t0, the starting time. So this is t equals t0, this is t greater than t0, this is t much greater than t0. And basically the atoms will spread out. Uniformly. Okay, so let's review what we did. We have a thin copper wire stretched out along the x-axis. A few of the copper atoms located near x equals 0 are radioactive, and these atoms can then jump to an adjacent lattice site at a high temperature, either to the right or to the left, and the lattice sites are separated by a distance L, and the time it takes to between jumps is tau, and the process is called diffusion. And right after the temperature is raised, we start watching the diffusion of the atoms, and we denote P of x dx, the probability that a radioactive atom is found at a distance between x and x plus dx after a time t, and t is much greater than tau. So we're going to sketch this probability distribution shortly after t equals 0, after a moderately long time t, extremely long time t, and we will find the mean displacement and standard deviation of the displacement. So I'm assuming the total wire length is 2L. The probability of a jump to the right or to the left will be the same. It's 1/2. There is no preference for the direction here. So I started from part B. So the total number of displacements I will have is t divided by tau. So there will be a total of capital N jumps, which is t over tau. And since the radioactive atom can jump to the right or to the left with equal probability, the probability distribution function should be symmetric around x equals 0. N is number of jumps to the right, n prime to the left, and n prime is capital N minus m. The total displacement to the right is number of displacements to the right minus number of displacements to the left, which is net number of displacements to the right, and each displacement has a length L, so it is 2n minus capital N times L, or 2n minus t over tau times L. Since the probability distribution of x is related to n, so there's one-to-one correspondence between n prime, and x. The probability distributions are the same. The mean value of the displacement will be the integral over all possible values of x, x times the probability distribution function p of x dx integral, and that should be 0 because you're multiplying an even function with an odd function and integrating around 0 with a symmetric integral. You will get a 0 at the end. And as for the standard deviation, which is by definition deviation from the mean square bar square root, or root mean square, since the mean value of the displacement is 0, delta x is equal to x, so standard deviation is x square bar square root. And since x is 2n minus capital N times L, it is L times square root 2n minus capital N square mean value. X bar is 0, so 2n bar minus n is 0, so n bar or n prime bar is capital N over 2. And p and q are 1/2, so n bar is capital N times p. You can see this by defining a variable u which has a value 0 if there is no right jump, and it has a value 1 if there is a right jump. So it's the sum of these ui values for all jumps here, that is n bar, and it's going to be equal to 0 times q plus 1 times p for the mean value, so it is p. So it is either 0 or 1. And basically you might think that ui should be equal to -1 if there is no right jump, there is a left jump. Well, I'm not counting the n minus n prime here, so it's not the m value that I'm looking at, which is the net number of jumps to the right. So that would be for m. So you would have to define a -1 and +1. But here it is 0 and 1. So we have n bar is equal to capital N times p, and similar to what we did in the lecture, the delta n square bar is then can be calculated using this definition, and also looking at the definition of delta n square bar, you can write this as an explicit summation over delta ui square and delta ui delta uj product summation, and finally we show in the lecture that delta n tilde is square root n pq. So delta n tilde is n minus n over 2, capital N over 2 square bar, which is square root n pq, which is square root n over 2, or if you square the both sides, it is n capital N over 4. So you can see that 2n minus capital N divided by 4, 2n minus capital N squared divided by 4, average value is n over 4. So 2n minus n square average value is n, which is t over tau. So we have therefore for square root of x square bar L times square root n, which is L times square root t over tau. And I would like to remind you that this is basically a binomial distribution we have here for n. It's similar to the previous problem where we had the random walk, where we choose n steps out of total capital N steps. P to the n, q to the n prime gives the probability distribution of n. In the continuous limit, this basically turns into a Gaussian distribution, which is 1 over square root 2 pi standard deviation of n exponential minus 1 over 2 n minus n bar over delta n tilde square. That's the Gaussian distribution. And the answer to part A is you have a Gaussian distribution with a very narrow full width at halfbacks at the beginning. For a moderate time, you will have a relatively wide full width half max in the Gaussian distribution, and eventually you will find that the atoms will spread out and you will have more or less uniform distribution of radioactive atoms in the long time limit.